We'll start up inductance, do RC circuits, and cover some energy density stuff. And before we do, I've been wanting to get these demonstrations here. All right, so what do we have here? We have a coil, right? And this is an ammeter. So coil, I have a magnet here, so if I put this through, changes the magnetic field in there in the coil. So what will that do? That will induce some current, which will basically in turn induce some EMF, and you should see this meter move. So if I was to slight movement, it's not as profound as I was hoping. You guys can see that, right? Little wiggle. With a little wiggles, but still, you see the point. I mean, you need a bigger magnet than this to get things going. This is a stronger magnet than that. Okay, just a heavier rod. There we go. What did it go up to? So let's see if we can get up to 10. Nah. Yeah. Again, this follows Lenz's law also. Do they? Yeah, but we'll go through that in a bit. All right. So yeah, we have a couple of fun demonstrations here we'll go through. So far we covered induction, right? We covered pretty much most of the aspects from it. We covered Faraday's law. We know that Kirchhoff's law is just a special case of Faraday's law. So from now on, you can just apply Faraday's law for everything. So today I'll quantify the ability of a circuit to fight the magnetic flux, right? And the magnetic flux that it fights is produced by these circuits themselves. So if you have a circuit and you run current through it, what's going to happen? You produce a magnetic field, right? So when you create the magnetic field, Faraday's law dictates that you have to have, the opposing something to fight that change in current. So we call that induction. So there will be an induced EMF in the circuit that fights the change in current, that fights the change in EMF. And we express this as this quantity as L, right? And we call L as self-inductance. Right, and the self speaks for itself. The circuit is doing that to itself, right? It's trying to fight the change, and the magnetic flux that's produced by a circuit is always proportional to this. It's always proportional to the self-inductance, and we know that it includes current, the magnetic flux that's produced. So we can say magnetic flux is equal to L times I. And so what this L, this self-inductance, what this is essentially a proportionality constant here. Right? So this is dependent on the circuit. Now, get back to this. There's also another concept called mutual inductance, which we'll do towards the end of the lecture, and that's also fairly interesting. All right. So I have what I call here my magnetic flux, and I'm saying that it's proportional to some constant self-inductance times the current. right? And we also know that my induced EMF is equal to what? Faraday's law says it's equal to negative d phi b dt, right? It's equivalent to the negative change in magnetic flux. Again, this negative sign is just Lenz's law. So it's just showing that it's fighting it. So now we can say that this is equal to, so this is my magnetic flux. I'm looking at the change in magnetic flux. So I'm essentially looking at negative d over dt Li, right? What did I say L was? L was a constant, right? So I can pull this out of the derivative. So I have negative L di dt. And this is equal to the induced EMF. Now L, like I said, is only a matter of geometry. It doesn't actually depend on the current itself. It's just, it depends on the properties of the circuit, and so on. It depends on the solenoid in the circuit, and if it has actual inductor in the circuit, it depends on the physical properties there, but not the current. So it's more of a geometric property. So now let's go back to our trusty solenoids, which I said were so interesting in the beginning, and let's look at a simple example. So let's say I have where are my markers? Here they are. All right, so let me look at an inductor to begin with. Sorry, a solenoid. So it's the same solenoid more or less we looked at before, right? This is closed off. I have some current being propagated through there. The radius of the solenoid here is of the windings, let's say, is small r, and the length of the solenoid here is L. And this is a solenoid that we're calling it's part of a circuit. It's a complete circuit now, and this has some number of windings and windings. And you may remember from what we calculated from last week from Ampere's law that the magnetic field inside a solenoid is mu naught I n over L. And of course, we discussed this at some length. N over L is the number of windings per meter. Right? This is windings per length, so it's windings per meter. Now, if you attach an open surface to this, again, it's kind of difficult to imagine what the surface would look like, but we can use the soap trick we discussed. It's going to look like a staircase, a helical staircase, a spiral, helix. And we know the magnetic field doesn't go in that direction. So we attach the open surface. We know the magnetic field penetrates that surface, right? So what's that going to do once the magnetic field produces it or penetrates it? We know we have flux, right? Because the flux, magnetic flux, we know is also proportional to the surface area of those loops. Is right times the whatever magnetic field, the strength that goes through there. And we're making an assumption here. We're assuming that the magnetic field inside the solenoid is constant, and we're assuming that the magnetic field outside the solenoid is zero, right? And it's a fair assumption. We saw the field lines last time, although, like as it happens many times, these demos don't work out as well as I was hoping they would. We still saw the field lines clearly inside, but outside, just around the wires, we saw a small amount, but other than that, it was non-existent. Right? So it's a fair assumption to make that outside the solenoid, the magnetic field is zero, and that sort of simplifies our lives. So from this, we can say that the magnetic flux here is equal to pi r squared, right? That's the area of the surface area of one loop, times the number of windings, and of course, it's going to be squared mu naught I over L. Right? And this is going to be equal to Li, as we said up there. Right? So this is my magnetic flux. that equals to Li. And this is the definition for self-inductance, L. That's a good question. It is squared. Yeah, so this magnetic field itself has n in there, and we have a number of loops. So if you take one loop, you have this magnetic field because you're looking at the density of windings per length. And then you have n number of windings, so you multiply n times for the flux. So the flux, the magnetic field sort of depends on how long it is, but the flux doesn't actually depend on the length, if you remember when we discussed it. Right? So the flux is just how many loops you have and how many times the magnetic field is penetrating it. So that's why you have the n from the surface area or from the flux, and then the n from here that gives you n squared. So saying this is self-inductance. Right, so from here we can calculate what L is. L I just divide by I there, so I get pi r squared n squared mu naught over L. The i's there cancel out. Right, so this is my self-inductance in a solenoid. Now let's put some numbers to this. So we looked at an example before where we took n to be 2800, right? 2800 windings for the solenoid. So let's look at that. So we have n is 2800 windings. The radius for this is 5 centimeters, and the length is 0.6 meters. And this is actually a common solenoid that they use in industry. And this is precisely the example we looked at last time. So for this, if I plug in the numbers, I get L is 0.1 henries. Right? This is the same as volt second over amperes. Henry is the unit for self-inductance here, and it's named after an American scientist. I believe it was Joseph Henry. Right? Usually, you see, circuits, normal circuits. You have self-inductance on the order of micro to nano henry. So you're looking at really small quantities, and so basically every circuit has self-inductance, right? Whether you have a solenoid in there or whether it's just plain circuit that's closed, you will have self-inductance, right? It may be very big in the case if you have a big solenoid or something, or it may be very small to the order of nano or even smaller. But every circuit does have inductance. You just tend to ignore it. So if you remember the first half of the course, when you had your Kirchhoff's laws and all the other circuit stuff you're doing with the IR circuits or just normal RC circuits, right, with the battery, it always said, in the book at least, it says ignore self-inductance, right? So that's why. You're ignoring that case because you weren't equipped with the tools to deal with it yet. And you didn't have solenoids at the time, so it was more or less reasonable to ignore it. But now that you know what induction is, what inductance is, the circuits, you have to take that into account. And we'll go through the circuits. All right. So like I said, even a simple circuit, you have something with just some current going about, right? This will produce a magnetic field, which will in turn give you an inductance. Right? Therefore, always has self-inductance. Let's look at another proper circuit, and let's go through that. So start off with some battery. Here's my minus plate, positive, right? Some EMF of voltage V. I have an inductor, and here I have a resistor. This inductor is L, resistance is R. So again, inductors you draw with those little loops. There are different conventions, as some of you may know. For instance, in the United States, it's not uncommon to see something like that when circuits are printed, like little bumps. Europe mostly uses this notation, and I guess this notation is also not that uncommon here in the United States. For resistors, the standard zigzag is common here, but in Europe you'll just see a rectangle for the resistors. So you have different notation than just for resistors in the same way you have different notation for this. But more or less you'll see these loops. But don't be surprised if you see something like this in some book. All right, so we have our circuit, and what I actually forgot to do was draw a switch. So we have a switch now. Sorry, you guys have to erase. It's easier for me to erase on the board than for you guys. All right, so now I have the switch, and I close the switch at time t equals 0. And the moment I close the switch, so until now the circuit has no current flowing through it. So the moment I close the switch, I'm going to say at that time my current flowing through is also 0. Right? Because there's no current running prior to closing the switch. Now, what's going to happen once I close the switch?
You have closed circuits, so you have EMF from all through the loop, you have current.
Right. So is the current just going to shoot up to what it is? No, right? So in principle, what's going to happen is it's going to increase slowly. Right? So increasing current or changing current gives us a exactly. We get inductance from it. We get a change in magnetic field that gives us inductance. So again, Lenz's law dictates that the inductance will fight the change in current, right? And it's gonna, I want to go through this, but it's gonna fight it. So there comes a time when L will, or in self-inductance, will lose the fight, and the current will reach its maximum value. And the maximum value is usually dictated by Ohm's law. So if I have V here, I have R here, V equals IR. Therefore, my I max, maximum current that maximum value that the current can reach, is equal to R V over R. In your book, you'll see current from this stage on, or even a little bit before, represented by a small lowercase I. Right? If you guys see the book. And this essentially, lowercase I essentially means it's time dependent, this current. I got in the habit of using this notation where I use uppercase I for both time dependent and time independent. But just assume that when you have something like inductors and all that, we're essentially dealing with time dependent current. So essentially it's a function of time, because it changes with time. It doesn't start off at I max, it's not a constant value anymore. We're looking at time derivatives of it, so it's going to change. So again, in this case, we have a resistor here. Let's assume that this self-inductor I put in there has no resistance. So think of it as superconducting. So that it doesn't take up any of the energy. So let's look at a plot of how the current's going to look like with respect to time. So I have time goes here, my current goes here, and let's say this is my asymptotic limit for current, which is V over R, that's I max. Now you can expect, looking at the equation for this, for my inductance to be something like that. Now it will slowly approach, or my current to look something like that. However, if I have a really high self-inductance, what's going to happen? It's going to fight the change in current that much harder, which means that the current will rise up much slower, and it'll take a lot longer to get to the higher value, to the I max. This is with high inductance, self-inductance. If I have really low self-inductance, I can expect it to look something like this, right? It's going to peak really fast, and then of course it will reach its asymptotic limit. In principle, if I don't have any inductance, which I just convinced you a few minutes ago was never the case, if I didn't have any self-inductance, as soon as time 0 the switch closes, I reach my maximum value, right? But we know that that's not the case, only the spherical cow approximation, if you will, but we know that's not really the case anymore. So we did this more or less on gut instinct, based on what we think it would look like, right? Now let's calculate this out. Well, it'd be helpful to have those two down. So what do we use to go around the circuit now? Yes, very good. Well, I mean, I just told you guys a few minutes ago, at this point you just use Faraday's law. Now, it's kind of an abomination that some books, including the university physics book we use, the way they approach this formalism is they essentially take Kirchhoff's law, right? And the convention they use is, okay, we have, if we're marching about in the direction of current, then the voltage drop or the potential drop across an inductor is minus L di dt. If I'm going opposing to the current, they say the potential drop across an inductor is plus L di dt. Now, let's look at this real quick. So I have, let me redraw this, minus positive. Well, this stage the switch is still open. Right? Voltage, induction, inductance, and resistance. Now, over here, I have my electric field going from here to here. Right? And over here, I have my electric field going from here to here. This, however, has no electric field, because I said this doesn't have any resistance. Right? Therefore, the electric field is 0. So when I march around, yes? Oh. So it's closed now. When it's closed. We're looking at the case when it's closed. Sorry. Yeah. So assuming there's current flowing, we have some electric field. Right? And this has an electric field, this has an electric field, this does not have any electric field. So the notion that Kirchhoff's law actually applies to this and is valid is kind of absurd. And not just your book, but pretty much almost every textbook I've encountered does it. I don't think Dr. Baskis's book does that. I need to go back and check. But most of the books assume that this is the case. And I'll show you why they say that. But of course, we're smarter than them, right? So we know we have to use Faraday's law. So E dot dl equals negative d phi b dt, which is equal to negative L di dt. Again, this is a function of time now. And we, of course, know Kirchhoff's loop says, if I go about Kirchhoff's law, it says E dot dl equals 0. Right? We can't use this. Now let's write the loop equation for this. Let's go around the loop and write down what we get. So my current will obviously be flowing this way, and usually I always start off, or I march in the direction of my current, and I'll show you why. So when I go through my current in this direction, I get, well, let's start off with this. I get IR minus V equals negative L di dt. So when I march in the direction of my current, I always get my EMF equals negative L di dt. If I march in the opposing direction, this would be a positive, but then you just have to adjust for that here, right? So you can either take that sign into consideration or just go in the direction of current and don't have to worry about the sign. But that's just a suggestion. You can go around however you want. All right, so we have this, and this is the only correct way to go about it. We need to apply Faraday's law for this. Now we can express this a little bit more differently to make it seem a bit more intuitive. I'll bring my voltage, I'll bring my inductance over there. So what I have here is going to be L, well, no, let me do it the other way around. So I'll bring the voltage over to the side, so I have V minus L di dt equals IR. And this is sort of, at least logically pleasing, because I have a certain EMF, and this term essentially says that my inductance is opposing, it's fighting my EMF, which we know is the case right now. So this is a bit more intuitive way to look at it. And of course, if I don't have any self-inductance, which again is never the case, but if this were 0, then I just simply get Ohm's law, which is V equals IR. So let's solve this differential equation. And to solve the differential equation, usually we bring everything to one side, and then look at the equation. If it's first order, then we probably usually go about either by separation of variables or one of those other techniques you learn in your differential equations class. If it's second order, at that point we just guess the solution, because we know it has to look like a certain form, so we just guess it. All right, so let's bring this over. So I get L di dt plus IR minus V equals 0. Now, this is precisely why the books think they can use Kirchhoff's law and get away with it, because they, if you look at this form, it looks like Kirchhoff's law applies. You have some change in potential due to the inductor, due to the resistor, and the EMF, and you set that whole thing equal to 0, which is what Kirchhoff's law is. But this may look okay, and most books do it this way, so I'm not going to penalize you guys for going about doing it this way. But I just want you guys to know that to approach this using Kirchhoff's law the way the book does is fundamentally flawed. All right, so we know that this is a first order differential equation, so it shouldn't be too difficult to go about trying to find the solution. So first thing I would do is separate it out. And I mean, I'm sure you guys have seen or solved this equation in 218. Maybe now you don't have current and inductance, but you have position there instead of current, but this changes with time, and you had some spring constant or something else that may even have friction, right? So I'm sure you guys solved something like this in 218. So this is not a new equation, it's just different parameters. So let me divide both sides by L. So first now I get di dt plus I R over L minus V over L equals 0. Right? So this I can express as di over dt equals V over L minus IR over L. Right? Now I apply my initial conditions. I know that at time t equals 0, my current is 0. Right? So therefore, when I apply this, di over dt at t equals 0, my current is 0, so I have V over L minus 0 R over L. This goes away. So I know that in this case here, this is so this gives me that. Now the next condition I know is that at time, as time approaches infinity, at t going to infinity, I approach the I max, right? My current approaches I max, which is equal to V over R. So at I going to infinity, I know this is equals to V over R, which is my I max. Therefore, di over dt at time going to infinity, I have my, let's see, so from this I get, I substitute in for the voltage there, so I get I R over L minus I R over L, and this equals to 0. And again, I know that when this approaches, my current doesn't depend on my inductance. So now I can rearrange this, and I get di dt equals V over L minus I R over L. Right? I can divide by I, so I get, I can multiply both sides by dt and divide by I minus V over R. So I get di over I minus V over R equals negative R over L dt. I integrate both sides, and again this goes from, well, not yet, so hold on. Yeah, so my time here goes from 0 to t. My current here goes from 0 to, let's say, some current I prime, or I, whatever current you're looking at. So now I have this equation essentially boils down to natural log of I minus V over R over minus V over R equals negative R over L times t. So now I go solve for I. Solve for I get I max, right, which is basically V over R, times 1 minus e to the minus R over L t. Right, so this is my current equation. And it satisfies my condition. As time t is 0, this term becomes 1. Is it? Sorry, at t equals 0, this becomes 1, so you should get, wait a minute. Yeah, 1 minus 1, that's 0, and that goes away. At time t goes to infinity, so this whole thing is negative, so as this increases, this approaches 0, so you just get the 1 here, so as t goes to infinity, you get I max. So it satisfies my initial conditions. So we're good. And so again, you expect something like that. Now, an interesting case to look at is when the time t equals L over R. And actually, I think it's given a relaxation time or time constant in your in the textbook. So it's interesting because when time is this, once I plug it into the equation there, I get I is approximately 63% of I max. Right? If I double this time, if I look at t equals 2L over R, then my current is approximately 86% of I max. if I was to look at a plot of this, this is my asymptotic limit, V over R, current, my time, and normally it approaches something like this. If my inductance is low, it goes up there. And if it was really high, something like that, right? Now what I'm looking at here essentially with time L over R is when it looks like 60%. So this is my L over R. This is going to be approximately 63% of I. Now, let's look at a case when we don't have the EMF in the circuit anymore. Now it's hiding here. So we're looking at the case. Well, again, on a board, I can just erase this. Right? And the switch is closed. So I'm looking at this circuit. I just have the inductance and the resistance. Right? So now what happens? So if you want to think about it, now you can think about it as just me removing the battery and the circuit, the loop is still flowing. So at time t equals 0, my V is 0. So I'm defining my new 0 time. So what's going to happen now? Well, the inductance, self-inductance, doesn't like the fact that the current is going to go down. Right? So why it doesn't like the changing current. It doesn't matter if it's going up or down. So it just doesn't like the change. So because it doesn't like the change, it's going to fight it. So it's going to prevent the current from going down as fast. So you expect the current to, well, not go down right away. So before, when we when we weren't looking at inductance, you took a power supply out of the circuit, what's going to happen? You'll have no circuit because you have no EMF. Reasonable. But now you have inductance, so even if you take the power supply out, you still have a certain amount of current. So I shouldn't have erased that plot. Okay, so we have something like this, right? Here's my I max, right? V over R. So this is when I take the circuit out. So once it's at I max, let's say, and then it's not going to go. Normally you would assume that it just drops to 0, the current. This is current, this is time, but in fact, it's going to do something like that. So it's going to go down. I mean, granted, it's going to go down exponentially, but still, it's not instantaneous. So it's going to die off, taper off slowly. And how slowly? Well, it depends on how large the self-inductance is. If it's really large, then this won't taper off as fast. If this is almost non-existent to a point where it's 0, then you can expect it to taper off, or not taper off, but just drop to 0. And that, again, that's logically pleasing. We know we expect this solution. So again, at time t equals 0, I mentioned that I equals I max, right? And this is equal to my V over R. As time approaches infinity, I know my current is going to be 0. Now, as the current goes away, it's going to dissipate in terms of by heat from the resistor, and we know that that's along the order of I squared R joules per second. Right? What's joules per second? Watts, work done, and so that's not unreasonable. So it dies off at I squared over R, or dissipates as heat at I squared over R, until the current completely goes away to 0, and then the whole show is over. we're done. Now, but we need to look at the exact behavior when we make the potential, the EMF 0. So what was the differential equation we had before? We had L di dt plus IR minus V equals 0. Well, now we're saying that this term is non-existent, so this is what we end up with, right? L di dt plus IR equals 0. Well, this is more an easier, or more trivial thing to solve for. It's bring this over to the other side, so you have L and divide by L. So you have di over dt divided by I, so you have 1 over I equals R over L. Right. So if I'm looking at this, I have di. Again, when I multiply both sides by dt, that's sort of like a mathematical abomination. But yes, am I missing a negative here? Yes, I am. Thank you. But yeah, so that also is a mathematical abomination, but we won't get hung up on my mistakes. All right, over I equals minus R over L dt. I integrate both sides, and again, this goes from 0 to some I, and this goes from 0 to whatever t we're looking at. So the solution I get now is I get natural log there. Natural log of I, 0 to some I, equals minus R over L t. I take the exponential of both sides, so I get I equals e to the minus R over L t. Right, so this is my current behavior now. And again, I know my initial condition is that I is 0, or sorry, t is 0. This term goes to, forgot my coefficient here. I would have I max. So that when t is 0, what would I get? When t is 0, this term becomes 1, so I get I is I max, which is again what I was assuming would happen. And as t goes to infinity, this would die down to 0. Again, this is what I was expecting would happen. Now the other constant we looked at t equals L over R. In this case, I get something to the effect of 37% of I max to remain still. Right, so I keep erasing the plots. So I have something like this, asymptotic, right, approaches that, goes down. So if I'm looking at that, this is my L over R t, this is my 0, and this is 0.37 of I. So again, this is a consequence of the fact that the circuit can fight its own magnetic flux that it creates. Again, self-inductance, it's doing it to itself. And all this time that the current is dying off, heat is being produced at I squared R. Right? It's power coming from the battery usually. So even when the battery is in place, you still see it dying off because of the resistor as I squared R. And when you take the battery off, you can still see the current in the circuit because of the self-inductance. It just doesn't die off. And this means that while the current is dying, again, heat is still being produced through the resistor until the current goes to 0. So where does the energy for this come from? For the heat? Well, not just for the heat, but for the current to stay in place. Exactly, it comes from the magnetic field that is present in the solenoid, which inductor here is basically the solenoid I'm calling. So there's a magnetic field there, and the energy is present in that magnetic field. And the idea that we have energy that comes out in the form of heat which was earlier in the form of a magnetic field, allows us to evaluate now what we call the magnetic energy field density. Handful to say. Magnetic energy field density. And let's look at an example of that. So let me first calculate how much heat is produced as I goes from I max to 0. So in this case, when it starts off at time t is 0 and goes to infinity, so my current's at I max and it goes to 0. Right? So at any moment in time, I know that the heat being produced is I squared R, right? So it's a function of time. So if I was to look at the total heat produced as the current dies out, I would have to take an integral. So I know that heat being produced is I squared R, and I'm looking, and this is in terms of joules per second. So I want to look at the total aggregate, so I take the integral of time going from 0 to infinity as dt. I plug in for what my I is here. Again, I had it up there, it's I max times e to the negative r over L t, right? So I get I max is a constant, r is a constant, so I can pull those out. I get I max squared, which is v over r, times r here, integral of e to the negative 2r t over L. Again, this 2 comes from squaring my current. Right? Don't forget that too. I was actually doing this calculation last night and I forgot to carry over the 2 and kind of messed me up. So don't forget that too. So this essentially, again, dt, forget my integral element. We know that this effectively comes off as L over R, L over 2R when I integrate it. Right? So from 0 to infinity. So now I get, when I plug in for the resistors here cancel out, so I get I max squared times L over 2. All right, again, this whole thing comes off as heat. I can now calculate how much energy there was per meter cubed because of the magnetic field, or because the magnetic field was exclusively only inside the solenoid. Right? We made the assumption that the magnetic field outside the solenoid was 0, so we don't have to take that into account. And I erased that a long time ago, but I know my current, I know my magnetic field B was mu naught I n over L, and this essentially is I max, right, my V over R. And I know what my self-inductance was. I calculated that also a long time ago. My self-inductance for this is pi r squared n squared over L mu naught. I believe this is the length, L. So let's do small l for that. So I know that 1/2 L I squared from this equals b squared over 2 mu naught pi r squared L. And this, again, is the volume of the volume inside the solenoid. So volume where the magnetic field exists, or volume where I'm saying the magnetic field exists. Because we're assuming the magnetic field outside is 0. This cell is supposed to be also little l. Sorry. Thank you. So we can see that we have a result for the, or we can come up, once we plug in stuff, come up with the result for the magnetic field energy density. So that is going to be b squared over 2 mu naught, because this is b squared over 2 mu naught times the volume. So I divide out the volume, I get the magnetic energy field density, or magnetic field energy density. So in principle, if you know the magnetic field everywhere in space, you can integrate over all space, and you can calculate how much energy is present in a magnetic field. And you did something similar in the first half, where you calculated the electric field energy density. Did you guys do that? Remember doing that vaguely? Right? I mean, we know that, it's something to the order of 1/2 epsilon naught kappa squared. Again, this also is in joules per meter cubed. And this represented the work I had to do to arrange the charges in a certain configuration. Right? In the case of magnetic field, it represents the work I have to do to get the current flowing inside a pure self-inductance. Right? So by pure, I mean that resistance R equals 0. So it's superconducting, if you want to think about it. And it takes work because the solenoid, or the self-inductance, will oppose whatever current is trying to build up in there. So I have to do work for it to change it. A good example is, well, not a good example, but let's look at some numbers for this. Should we take a break? Yeah, let's take a 5-minute break and then look at some numbers. I actually had this discussion with my old undergraduate professor, and about basically, of course, like the trains, and also having an vacuum chamber, but it would have to be like a straight shot from here, LA and New York Road. And what he actually said was, he discussed it with a friend who worked in the transit authority or something. And I guess the problem they encountered at the time was that they can't carve out a straight path from LA to New York that doesn't go underneath an Indian reservation. So, have to do up science.
They're building one in Colorado right now.
Are they?
The Tesla guy, what's his name? Elon Musk.
Oh no, Elon Musk. Yes. So he suggested the same thing. He suggested the vacuum thing. But then the system is a bit different. It has like some sort of rotary system where you basically load people onto the train. You get sort of like those vacuum things you see in stores where they pack up their money and put it in the thing, and just sucks it up. So that's the system he's looking at. But also that will of course require levitation.
Maintenance process on that would be that big.
You gotta keep the car. Not running the car. You need to keep the vacuum pumps running. So that's, yeah, everything has its but yeah, California I think is looking into the system by the German system, the Transrapid system. So hopefully that gets built soon. All right, so let's get back to, and we'll actually discuss levitation a little bit. This Elon Musk guy is actually, the guy's amazing. Came up with PayPal, came up with Tesla Motors, came up with SpaceX. I mean, pretty much anything he touches is turning into gold. Have an inductor. All right, so what I have here, I have a car battery, so that's 12 volts, attached to a resistor, that's 4 ohms, right? A light bulb, which is 6 ohms. There's light bulb 1, this is light bulb 2, this again is 6 ohms. And this self-inductor has 30 henries, which is a lot. And this has 4 ohms. In the internal resistance of that thing is 4 ohms. And I put that here just to stay consistent with this bottom part of the circuit. So when the switch closes, the first light bulb, the current flows through here, almost instantaneously comes on. Right? I'm saying almost because there is a hint of self-inductance there. Because over there, the self-inductance would be something to the effect of order of microhenry or nanohenry even. But this, in the second one, it's pretty large. The inductance is pretty large. It's 30 henries. So we can actually calculate how long it takes for that light bulb to light up. So we know that it's to the, if we look at the time L over R, right, which we know L is 30 henries over there, 30 henries over the total resistance. You have 6 and 10, sorry, 6 and 4, that's going to be 10 ohms. So this is going to be something to the order of 3 seconds, right? So it takes 3 seconds to achieve about 63% brightness on that bulb. And even when you look at twice this, right, that's going to be 6 seconds. It is still something to the effect of 80. What was it? What did it say? 80 something percent? 81? 86. 86% of the maximum, right? But since the light is proportional, it's proportional to I squared R, right? The light is, it's going to be approximately 75% at 9 seconds. Because it's not just simply a ratio of 1 to 1 here. You're looking at the square of that. So you have 75% brightness approximately at about 9 seconds. And the maximum you'll see here is about 90% because you have the resistance there and part of it will die out. So this is basically a, if you want to look at it, it's just basically an RL circuit, right? And we can actually even simplify this further. I should not simplify it, but let's change the terms a little bit. So we're looking at DC here. Let's make it alternating. So alternating basically means that my potential EMF is changing all the time. So I'm starting off with an AC power source. So the little circle with the squiggle in the middle, that basically means it's an AC current, basically. So I have some inductor, self-inductance here, and we here, if it's some alternating thing, we'll have some maximum amplitude we'll call V naught, and it's a sinusoidal one, so I have cosine omega t. Omega is obviously the angular frequency of this. So if I go around this equation, the differential equation I get, again, I have to go around using Faraday's law, not Kirchhoff's law, Faraday's law, because I have inductance there. So I would get L di dt plus IR minus V naught cosine omega t. I basically took the same equation, differential equation from before, and just replaced my potential, my V, with what I have over there, and this equals to 0. The solution for this is not immediately obvious. It actually requires some calculation, so I'll just give it to you guys here. So my current, when I calculate it out, it's V naught over square root of R squared omega L squared cosine omega t minus phi. So this is not really a very intuitive solution. You can't really just guess this out. So omega L here has to have the same units as my resistance here, and it actually does if you go through and calculate it. This basically is these two are the same units. And right now you can see that this has picked up a new phase angle, phase shift, right? And the tangent of that angle, of that phase shift angle, is equal to omega L over R. And I know this is relatively new, so let's take some time to digest it. So again, if you look at the before, when we looked at the alternating current circuit, I think last time we looked at it, when we calculated the current from the EMF, it was more or less the phase was the same for both of those. But now we have the phi, which is a phase shift between what the voltage is and what the current is now. So if phi is 90 degrees or pi halves, my current is delayed by a quarter of a cycle, right? And basically that comes from the fact that the current comes after the voltage, right, because of the self-inductance. So that's why you pick up the phase shift, and that's because the self-inductance is fighting the current, so it's going to take some more time for the current to come about. Again, so it's not entirely surprising, but it's interesting to think about. Now, looking at the current, when I look at the amplitude term, R squared over the R squared plus omega L squared, they obviously have to have the same units, so omega L has to be resistance. And if you think about it, the higher the frequency, what's going to happen if the frequency is higher here? The current will be lower. Exactly, so the current will be, the maximum current would be lower. And the frequency is low, the maximum current would be higher. So if omega is high, then my change in current is also very high. So basically, if it changes very fast, then that induces an EMF, right? So that induced EMF is also going to be really high, and the current in turn that you get will be lower. And now if omega there is 0, what happens? If omega is 0 there, basically you don't have an alternating current anymore, so it just becomes V over R times cosine of the phase angle, right? So it doesn't change anymore, and that, of course, it doesn't oscillate with time. It's just cosine of some angle, so it's just it figures out into the coefficient. So it becomes the case that we looked at before, more or less. Now, if you look at just the phase angle over there, the phi, if omega is really high or really large, or even if L is really large, what's going to happen? So if my self-inductance is really large, what does that mean? Right, because the system has the ability to fight back the change. So it can delay the current, so you'd get a larger phase shift. So if your omega is really high or L is really high, you'd get a larger phase shift there. And remember, the EMF is proportional to di over dt. Now, to give you some numbers for this, let's say that my V naught, my maximum voltage there, is 10 volts. My R there is 10 ohms. And my inductance is 10 to the negative 2 henries. And in the circuit I'm looking at up there, my L and R, my self-inductance and resistor, are in series. So if I look at frequency of 100 hertz, then my omega, which is in radians per second, is going to be 628. Right? My omega L, which is also like resistance in ohms, it's going to be 6.3. And my I max in amperes is going to be 0.85. And the phase shift angle is going to be 32 degrees. If my phase shift angle is really large, let's say my phase shift angle is 89 degrees, or before we get there, if my frequency is 10 to the third hertz, then this is going to be obviously multiplied by order of 2 magnitude, so I get 6.3 times 10 to the third, and then this is going to be 63 because it's going to be multiplied by 10. This is going to be 0.16 I max, and this is going to be 81 degrees phase difference. If I go another order of magnitude up, if it's 10 to the fourth hertz, then this would follow along equivalently. I'd get 628 for this. I'd get 0.016 amperes for this. So this is already like 50 times smaller than when I had 100 hertz. And my phase shift angle here is going to be 89 degrees. So actually quite interesting to see. So if your frequency is really high, or if your angle is, phase shift angle is really high, then your current's going to be really low, and then the resistance obviously would be high as well. Now let's look at this demo real quick. So what I have here, coil, a little power source with a button, so when I press it I get current going through, and it's plugged in there. So I have a couple of these rings. So even before we do that, let's look at this. This goes into mutual inductance. We haven't talked about it. I don't think we'll have time to talk about it today, so we'll do that on Monday. So when I hold this, I have current going through the coil. So when I put this in, you guys can see this, right? So it's basically, if you want to think about it, this is a solenoid. There's another solenoid. So this solenoid is inducing current on this solenoid, and that's called mutual inductance. And for those of you guys who have electric toothbrushes, right, when you plug it into the base to charge it, there's no electric contact points. But if you've ever opened those toothbrushes up, right, you have basically in the toothbrush you have a coil like this, and inside the charger you have another coil like this. So when I put it in to charge, it gets a current, and that's how it charges. Now what do you think is going to happen when I put this piece of aluminum in here? What's that? Right, I mean in principle if I could modulate the current, I could get it to float, but because I can't, this would just shoot up. Almost. Let's see it again. So, but if I could modulate the current that goes to this, I could make it float. Right? Now, I have here a similar one, but with a slit through it. Nothing. The slit right there. Going vertical. So basically, this is not complete the circuit. So there's a big slit there. So I noticed the question you guys haven't asked here. This is alternating current coming here. So what happens when I initially have, let's say the current goes to its maximum, right? The voltage goes to its maximum. I have a certain magnetic field that's going to be induced here. But when the current is decreasing, going the other direction, the flux is decreasing, which means that it's going to get attracted, right? So why didn't it just go down? Same thing you guys saw in that YouTube clip. When you're looking at an electromagnet, you saw that the train was sort of held in place and not just getting attracted and then dropping. Why is that? What's that?
Because when you're dealing with two loops like that, you're always getting the Faraday's effect Lorenz's effect. It's always going to be opposite.
Yeah. So basically, you're right. You're on the right track. So basically, what you have here is, since the two opposing currents are going to be in opposite direction, they repel each other. But because you have self-inductance there, when the field does change, when the current does change, it's going to take some time. So there's a phase shift. It's going to take some time for it to more or less change its direction of polarity. So for a while, even if the current is going down, even if the magnetic field on whatever, let's say that this coil originally switches around, it doesn't change the field in this loop, for instance, if it were staying still. So let's, again, the secret here is self-inductance. The induced current is delayed by a phase angle, which we saw over, yeah, so I can write it again here. So there's a phase shift of omega L over R, right? This is equal to my tangent of my phase shift angle. So it is delayed over the induced EMF, right? The EMFs are immediately coupled, but not the currents. There's a delay in the current. So if I were to look at this, so let's say I'm looking at some solid plate here, and I have a loop here, and the current is flowing in this way. So which means that my magnetic field is going to be pointing down from this, which means that it's going to create a current. Because it's solid disk, it's basically eddy current, so it's really hard to predict where the current would be. But I know it's going to be in this direction, which means that my magnetic field is in the opposing direction. So what's going to happen now? Again, if I'm looking at it from the top, there's my eyeball. I'm looking at it from the top, so I see a certain current is clockwise and certain as counterclockwise. So if I'm looking at, start off with, if I'm looking at the current through the first loop, which is this one, this is the second loop, I'll say. If I'm looking at the current through the first one, I'd get something like, right? And I guess neater and nicer it's supposed to be, but this is, let's say, my current. Now the EMF induced in the conductor, so this is my current. I'll say that anything positive is going clockwise, and then this is going counterclockwise. So it's oscillating the direction. So one's going to go in one direction, and it's going to change directions. The EMF induced in the conductor is going to look something like this, right? It's going to be shifted exactly by 90 degrees, because one's cosine and one's going to be sine. So I'd have something like this, so where I'd have my intercept there, another intercept there, another intercept there. So the phase shift between these two is 90 degrees. Now the induced current on that one would have to follow something along this way. So I'd have something like that for the induced current. So the induced current and this current aren't exactly lined up. So when this is clockwise and this is decreasing, this is still clockwise, but now there's a shift there, so it doesn't decrease right away. So essentially, more or less, that's what caused it. So when you have the magnetic field increasing, the current goes up in loop 1, right? And the EMF in loop 2 is in such a direction that it opposes the change in magnetic field to begin with. When the magnetic field goes down, the current would go down, and the EMF would immediately flip over. But the current has a certain phase shift, so you would still have attraction for a little bit longer, and then once that's over, then you still they're not synced up right in place, so at any given point you still have some amount of attraction. That sort of all normalizes because it's happening so fast. It's happening at 60 hertz, so it's about 120 times per second. So that's why it's able to still levitate, and that's exactly why those electromagnetic levitated trains from the trans-repeat system is able to levitate, not just bounce up and down. So I guess the Japanese system is simpler. You just have permanent magnets, so there's no alternating current. The alternating current would just propagate the train. But for that, you need to have some sort of lines on top. But for this, because it's levitating, you can just build in the driving force also. Anyway, so we'll do mutual inductance, LRC, and RC circuits on Monday. Have a good weekend.